All right, so I'm Adnan Darwiche, and I'll be talking today about a new advance on the algorithm of variable elimination. And before we get into this, let me give you the motivation. As we know, model-free supervised learning dominates a lot of what's happening in AI today in terms of applications, and people are starting to see limitations of that. And our interest is in model-based supervised learning, which is the contrast. And the reason we're interested in that is we want to be able to incorporate background knowledge into the learning process. The reason, again, is to be able to rely on less data, have robust systems, and systems that are more amenable to explainability, which are typically the complaints people have about model-free supervised learning. And the way we're going to do this is by compiling models, causal models, Bayesian networks with background knowledge into arithmetic circuits. I'll explain what that is in a little bit, but you can think of these as neural networks, but instead of being handcrafted, they are actually synthesized from models. And then we can train these using gradient descent as we do with the neural networks. Now, you can do this already today. So what are we doing here in this work? What we want to do is we want to represent these arithmetic circuits as tensor graphs, which is the standard way neural networks are represented. And if you do that, you get a couple of benefits. Major. One of them is speed. You can have order of magnitude improvement in terms of speed. Second is infrastructure. A lot of the tools that people have developed for supervised learning and neural networks like gradient descent are available in the context of tools that are based on tensor graph representations. So we want to take advantage of that. So what brings variable elimination into this whole story? Well, there are several methods for compiling models into ACs, and variable elimination happens to be one of them, and typically actually the more primitive one. But it happens that variable elimination also facilitates the use of tensor-based technology in a very nice way, as we will see. And this is why we got interested again in this, and we wanted to improve it and use it in a competitive way for this purpose. So what is variable elimination? It's been around for decades, and many algorithms out there are variations on it. The main ingredient of variable elimination is this notion of factors and their operations. And here's how factors look like. They're basically tables that map instantiations of variables to numbers. And the algorithm of variable elimination is about trying to evaluate expressions that look like this efficiently. So what we have here is these F1 through Fm are factors. I'm multiplying them, and then I'm summing out some variables from the result. We'll see what these operations are. But there are two main theorems behind variable elimination that allow you to evaluate this expression efficiently. All right, so we'll see that later. And what is the connection to tensors? Well, it turns out that factors are just tensors, and both of these are multidimensional arrays. It's just that when you say tensors, typically it means that I'm going to implement the operations on these multidimensional arrays in a parallelized fashion. So let's see, why is that even possible? Here are the two main operations on factors in the context of variable elimination. First one is called multiplication. I take two factors and multiply them. I get a resulting factor over their joint variables. Now, if you look in this case, and you see the numbers in the resulting factor, they're all independent, even how they were computed. So they could have been computed in parallel. Here's the other main operation on factors in variable elimination, summing out. I give you a factor, you remove a variable from it. So instead of having AB, you end up getting B. And if you look at the numbers in that resulting factor, they're also independent and could have been computed in parallel. So if you actually represent factors as tensors and use tensor operations, then you get to parallelize these factor operations. And this is not just on GPUs. You can get basically parallelization also on laptops, on CPUs, because of the more recent instruction sets that can take advantage of that. Okay, now let's talk about how all of this appears in the context of model-based supervised learning. So here's a Bayesian network model. You tell me I'm observing the variables A and C, and I want to compute the probability on B. You can compile this model and query into what's known as an arithmetic circuit that I introduced a couple of decades ago. The inputs here are these lambdas, which represent your evidence, and the other input is these thetas, which represent model parameters that get trained from data. The output is your query. And as I said, these can be trained from labeled data, and they can integrate domain knowledge in the form of independence from the causal graph, logical constraints, functional dependencies. So there's a lot of benefit to doing this. Now, if you look at this circuit, you would see that these operations, for example, could have been done in parallel because they don't depend on each other. Similarly, these guys, but when we do ACs normally, We don't take advantage of that. But if you represent the AC as a tensor graph, then you can actually parallelize these things. And this is an actual screenshot from TensorFlow of an AC represented as a tensor graph. And you can think of these nodes in the graph as being tensor or factor operations. They're doing a bunch of these guys in bulk and in a parallelizable way. Now, everything I just mentioned so far could have been done without this paper. You could have taken algorithm of variable elimination and used it to compile a tensor graph like this. So what is the contribution here? Well, here I have to make a distinction between integrating knowledge versus exploiting knowledge computationally. Integrating knowledge is easy from this point of view. Independence is already integrated, and logical constraints and functional dependencies typically take the form of fixing the values of some of these parameters, right? But what we want to do is exploit these computationally so we can minimize the size of the resulting tensor graph. Variable elimination already knows how to exploit independence or structure independence computationally. But what we are focusing on here is how do you exploit functional dependencies so as to minimize the size of the tensor graph. If you use standard variable elimination for this compilation process, you will fail on many interesting problems, including the ones that we have in the paper. And what we will show is 2 new theorems on variable elimination that allows us to exploit functional dependencies in a way that can reduce the size of the resulting tensor graph exponentially. So let's see how actually this works. But first, let me explain what is a functional dependency. It's simply a factor that says one variable is a function of another. So this factor, because of the numbers here, says that if you tell me what the value of X is, I know what the value of Y. And here's another factor also specifying a functional dependency from X to Y, but a different one, all right? And these kind of functional dependencies are pretty common in certain models, and these are the ones that we want to exploit. So to explain to you the new 2 theorems that we have, I have to tell you the main theorem of variable elimination, where it fails and how we improve on it. As I mentioned earlier, variable elimination evaluates expressions that look like this. You're taking a bunch of factors and multiplying them and then summing out some variable from that or multiple variables. Now, if you try to do this naively here, you will go and multiply these guys to construct a factor over 4 variables and then sum out the variable Y from it. The main theorem of variable elimination tells you don't have to do this. Because the variable Y does not appear in these 2 guys, you can pull them out of the sum and then sum out Y from this and then multiply. As a result, the largest factor you end up constructing is over only 3 variables. And in general, this can lead to exponential improvements in terms of computational time. Now, if I was actually summing out the variable X, then this theorem does not help me because X appears in all of them. In this case, I have to multiply all 3 and I have to end up constructing a factor over 4 variables. And this is where the new theorems and the main contribution comes in. So let's look at the same expression and let's assume that this factor is functional. It specifies a functional relationship from Y to X. There's 2 new theorems. The first says, and you can think of it as a replication theorem, it says you can replicate functional factors. So here's F, and I replicated it. And this product is the same as that product. Now, why would you not do this? That's because of the second theorem. The second theorem says, since these 2 components, both of them have a functional factor for X, and since I am summing out X, I can actually sum out X independently from these 2 components. And if you do that, the largest factor will end up being over 3 variables. And more generally, this could lead to exponential improvements, as we will see later. And the interesting thing here is this theorem or these results do not need to know the identity of the functional relationship. All I need to know is that this factor represents a functional relationship from Y to X, but I don't need to know the details of that function, which is pretty significant from a learning point of view, as it allows us to exploit functional relationships computationally, even though we don't know their identities. Of course, how do you put these 2 theorems to construct an algorithm? That's in the paper, code, examples, and so on. Let's go to experiments. We did 2 experiments in the paper. Both of them are about recognizing synthesized shapes in noisy images. One of them is for rectangles, the other is for 7-segment digits. We did have generative models for each case, and I'm highlighting here some of the variables that are functional. The ACs that are compiled from these models take images, pixels as input and output recognitions. And let's look at the benefits. This is one of the tables from the paper. And what you need to look at is here. What happens when I compile circuits or tensor graphs with or without background knowledge as exploited by the new theorems? This basically tells you here that if you don't exploit background knowledge, you're going to have to construct a factor over about 33 variables. But if you exploit functional dependency, the largest factor is over that many variables. This is dramatic here. Straightforward variable elimination will need about 140 variables in a factor, which is just unfeasible. And using the new theorems and the new algorithm, you can drop that to 19. Impossible, possible. The other interesting thing, which is the reward here, is evaluation times. Here's an example of an AC that has about 100 million nodes, and it can be evaluated in only 76 milliseconds, right? Because this AC is represented as a tensor graph and a lot of the operations are parallelized. We also have very primitive experiments on learning and the benefit of integrating background knowledge in the learning process. And as you will see, that sometimes with very little knowledge, I can get decent accuracies, which is the main benefit in this particular case and main motivation of why you want to do model-based supervised learning. Now, these are very primitive results. We have follow-up work, which will appear later this summer, which is dedicated to evaluating this from a learning point of view, in which we also compare with neural network. All right, so now we get to the concluding slide, which I will just highlight the last part of, and that is tensor technologies can lead to very significant improvements, and they can be very important practically, as we've seen, which is the main motivation behind this work. Thank you.